All right, welcome everyone. Thanks a lot for being here. I'm going to also talk about the travel mode detection, but in a bit of different context, in a different business use case that we have. So just for the statistical purposes, how many of you actually know what FAIRTIQ is? Can you raise your hand? Okay, there are a lot of people. That's really great. But if you don't know, we're also just to tell you, we've been also recently integrated to the SBB application. So that's many of you will probably know as SBB Easy Ride. So, but it's not going to be a product presentation, but I will just going to set the context of what we do to explain you the problem that we're trying to solve. So the way it works is that the application gives you access to the public transport. And it operates with a simple, swipe gesture, and after you start the app, it starts collecting the locations from you. So it periodically sends locations to our backend. And when the user stops the application, our goal is to correctly tell how exactly the user traveled so that we can later, afterwards, compute the right ticket price for the user. So how exactly, why we're interested at all in transport mode detection with this mode of operation? So the transport mode detection or travel mode detection is interesting for two purposes for us. First of all, if we know, for example, in the first segment that you traveled by train, we can improve the quality of our mapping algorithm. Then, for example, we don't need to search all the routes. We don't need to search the bus or the tram routes. If you know that you've been traveling by train, that improves the quality of the mapping because it's also not precise. And the second thing, which is really extremely important as well, is that we quickly realize that people do not people forget to check out. The app is running and they left the public transport and they forget that it's running, and they kind of stay in somewhere, or they walk, or they do something else, and we don't want to charge them for this, because the public transport tickets in many places, they have time validity, they have zone validities, and if we will be charging them for this extra time, they will get upset, right? So this is really the problem that we're trying to solve in our use case that arises really quickly, that we want to distinguish between the non-public transport and not public transport. So we don't want to distinguish all possible transport mode detection, because you saw that's not works great in all the cases, especially if you want to distinguish different modes of public transportation. But for us, the key thing was to distinguish initially between public transport and not public transport. So the way we did it, so let's start with really going to the machine learning here. So first we need obviously the data, we need to collect the data. And we started with these use cases that we saw when people forgot to check out, and with our employee data that we collected. And we simply have two labels. So each location, basically we label them with one of the two modes, except for the location at the border of the two modes. So this, again, is extremely simple. Label them so that each location belongs either to public transport or non-public transport. And the second thing that they go, now that we have every single location labeled, is that we split them into sliding time windows. So why exactly do we want a sliding time windows? Well, that's actually, we didn't invent this. Of course, that's a really standard technique, because you want sliding time windows because you want to really capture the moment of the transition between one transport mode or another. So, and the machine learning model then will be able to tell with, changing really the probabilities when your sliding windows change, how exactly, what is really the transition moment. And the two important kind of parameters to look after here is the minimum number of locations in the window and minimum duration in the window. So why is this important? It's because your locations, again, with when you change the transport mode, this duration can be different duration. So usually it happens kind of when you go out of the train, but you also want to capture kind of a lot of information from your window, because if you don't have enough locations or other sensor data in the window, then your model will not be able to be predictive enough for this window. But on the other hand, if you have a too large window, then you just miss, there will be a mix of two modes in this window at some point. So you want to strike a balance in this, in the duration of the window. And for us, it's around 3 minutes. And the second thing is the minimum number of locations in the window, because also like we don't control the delivery of locations to us. This is controlled by the mobile operating systems, Android or iOS, and they don't always deliver locations at the exactly precise time intervals. So you want to also strike a balance here. So now that you have you have your windows, you have several locations in a window, what you're going to do next? Well, we start with feature extraction, right, for the window. And there is a large body of research actually for the transport mode detection on how to extract the features especially for the speed, the standard ones. So the speed, the distances, location accuracy, so all kind of these features. And, you want to take different, statistical features such as percentiles, medians or standard deviations. And this all is really like important for the transport mode detection, because of course, like, when you walk, the speed is slower than when you're in a public transport most of the time. So just one thing I want to stop here at is that why do you actually want percentiles or medians? It's because of the location outliers. So if you ever worked with, with the data delivered from mobile phone, you could see that some locations are, 100 meters, 200 meters, or even kilometers off from where the person actually wants. So if you use, the statistical features such as averages, this will basically skew your results. So you want to have some sort of statistical features such as percentiles to get rid of these outliers. But the second set of features I want to briefly talk about that is not often mentioned in the literature, because they try to kind of understand all kind of means of transportation, is the domain data. So we have, because we kind of provide, already mapping to the public transport data, we already know these tracks, and, and the stations from the static timetable data. So this is really crucial to use this data for transport mode detection, the distances to the station or the closeness to the route. So this really gives an edge and improving, the last bits of accuracy, improving the model to, even higher levels of metrics. So the model that we took initially, so we were just starting with it. So we decided to pick random forest model, and actually any ensemble model would be great here, either XJBoost or extra trees model. So why we chose this is because it's, first of all, you cannot really do a lot of, like, if you want to experiment, this is really helpful because the model is very robust and it's quick to implement and expect and understand why certain results were like this. Because, for example, if you had problems in your ground truth data, you can quickly understand it from the random forest model to understand the features and let you relabel the data and then move to something else. And then, because we were starting again with this problem, we didn't have a lot of data originally. And this random forest model is really robust on only a few samples. You can see from the curves here, it's goes quickly to really high levels of accuracy, and then it's still, like with the more samples, it continues to grow on the cross-validation score. So let's look a bit what happened. So we deployed it around 1 year after the product, so somewhere in the beginning of 2017, and continued, to improve and collect data here. So this is what a typical day in FAIRTIQ Live looks like. In blue, you see the public transport, and in red, you see non-public transport data. So you can see that really, that's really true that a lot of people forget to check out, or, just they check in, and do something. They just want to prefer to have their ticket all the time active. And there is a large amount of, the non-public transport data. So we don't really want to charge for them. And this really improved our customer care cases. So let's look a bit what happened. So we deployed it around 1 year after the product, so somewhere in the beginning of 2017, and continued, to improve and collect data here. So this is what a typical day in FAIRTIQ Live looks like. In blue, you see the public transport, and in red, you see non-public transport data. So you can see that really, that's really true that a lot of people forget to check out, or, just they check in, and do something. They just want to prefer to have their ticket all the time active. And there is a large amount of, the non-public transport data. So we don't really want to charge for them. And this really improved our customer care cases. There is one bump here at 4 a.m. that you might wonder in what is this? Why there is a spike in in this thread data? So this is easily explainable. It's because we close. So when you run the app, we close all the trackers at 4 a.m. We do not allow trackers to run off after midnight, where midnight is 4 a.m. for us. Yeah, and obviously most of these trackers, people just forgot to check out, so they really have a lot of non-public transfer data. That's why there is such a skew in the data there. And the second thing I want to talk about are the specific case of funiculars. So after we deployed the model, we also had a monitoring on how many, like, if the person checks in at certain stations, how many empty journeys he has then after, like the journeys with empty, the trackers with empty journeys. So he didn't have to pay for the trip basically for this. And we noticed that in particular, some funicular stations got a large percentage of these journeys, and we started to wondering why. And the reason was that, a lot of funicular journeys were predicted as non-public transport because of their low speed, and because the funiculars usually go up, and we measure the ground speed with latitude and longitude. Yeah, so the speed was very slow. So we started to think, what we can do with it, and in the end we use the distance to the funicular pass in the end to see, because not a lot of people turn the app on just to walk or bike around the funicular. So most of the time they use public transportation, and with the more data that we collected and labeled, this really allowed to bring down this the amount of empty trackers there. So people now have to pay as well for the journeys that they do on funiculars. So what do we have now that it works really well, as you could see from my presentation? So, but what next? What kind of problems do we have? What are the future, where we want to move? So there is like a problem with the random forest model, so to say, is that our data is a time series data, right? And the way I showed you, the way we split this into sliding time windows, is that the random forest model, it doesn't know any history, it doesn't have a memory. So we basically label, and it does predictions basically on each window independently. And, it's natural that the modes, they depend on each other when you change. And also like the change of speed, it happens gradually, not immediately. And the random forest has no idea about this. So we want to see what can be done, to improve this, and we started to move towards the neural network models, such as with memory, the LSTMs. So this this is still an ongoing work, but what we saw, that it allows to really have a bit higher accuracy, but we had a bit of drop and recall on this model, and we're still investigating, because with now it's much harder to understand how the model actually makes prediction, why it made this prediction, what is the transition. So it requires a bit of more work to get here. So random forest model was a very good model to start with, but now we're thinking how we can do better than this, and what we can improve in specific cases. For example, the bus in the traffic jam, you don't know. Random forest will just say you're not moving, right? Because the bus is staying, you don't have a speed. But maybe with this, with other models, we'll be able to do better for such specific use cases. And hopefully, me or one of my colleagues will be able to tell you more about this at the next AMLD. So thanks a lot for your attention.